Good morning, good afternoon, and good evening to everyone, and thank you for joining today's webinar, What We Know About NanoEHS, How It All Began. My name is John Howard, and I'm the director of the National Institute for Occupational Safety and Health, and I have the pleasure of moderating the webinar today. The NanoEHS webinar series is an important platform for agencies participating in the National Nanotechnology Initiative. It allows us to share information on NanoEHS research, progress, and findings. Before I introduce the panel, I'd like to give you some background about NNI's NanoEHS research agenda and why this topic was to inaugurate the 2021 series. First, the federal government's commitment to health and the environment has been a central part of a nanotechnology research framework since the early days of the NNI. The creation of the Interagency Nanotechnology Environmental Health Implications Working Group, or NEHI, under the NNI was pivotal in charting a path to address the key NanoEHS research questions. The 2021 NanoEHS webinar series will focus on sharing what we have learned about the environmental, health, and safety aspects of engineered nanomaterials in the decade since the publication of the NNI NanoEHS research strategy in 2011. Throughout the series, experts will share the big take-home EHS messages in 6 broad topic areas with the broader nanotechnology community, and will highlight the NNI's role in answering research questions in each of these areas. This first webinar in the NanoEHS series brings together 4 pioneering scientists who were pivotal in the emerging field of NanoEHS in the early days of the NNI. We have asked our speakers to share their perspectives on how it all began and to discuss the robust community that has developed and continues to support current and future NanoEHS activities. Today, we're going to hear from Gunther Oberdeutzer, Professor Emeritus in the Department of Environmental Medicine, University of Rochester. Gunther's work has focused on the potential impacts on human health of airborne ultrafine particles and investigation of the biokinetics and translocation pathways of inhaled engineered nanomaterials. Second, Dave Rajeski is a visiting scholar at the Environmental Law Institute. Prior to joining ELI, he served as director of the Science and Technology Innovation Program at the Wilson Center. He also worked at the White House Office of Science and Technology Policy, the Council on Environmental Quality, and EPA. His work focuses on the interaction of public policy with emerging technologies. Third, Andrew Maynard is an associate dean in the College of Global Futures at Arizona State University. Andrew is a scientist and an author whose scholarship focuses on emerging technologies and their responsible and ethical development and use. Trained as a physicist, Professor Maynard's work cuts across areas of expertise ranging from the natural and social sciences to the humanities, policy, science communication, and the socially responsible and beneficial development of emerging technologies. Fourth, Vicki Colvin, Professor of Engineering and Molecular Pharmacology at Brown University. Vicki's research focuses on the synthesis and characterization of nanomaterials. Her interests include studying the potential application of nanoparticles for water purification and how nanoparticles interact with living systems. In 2006, she pioneered the use of water-soluble quantum dots in biomedicine. She served as Brown University Provost from 2014 to 2015. So welcome all four of our wonderful speakers. We have reserved time for your questions that you can ask to the panel. And what I'd like you to do is to type your questions in the Q&A box. Please try to refrain from putting them in the chat box so we can concentrate on one particular source, the Q&A box. We'll try to get through as many of the questions as you have with the panel as we can in the time allotted, which is 90 minutes. And I look forward to a lively conversation. A final comment before I turn it over to Gunter. I hope that you will join us for other NanoEHS webinars in the series. More information on all the NNI public webinars can be found on nano.gov. You can also follow us on Twitter at NNI Nano News. And now it's my pleasure to turn it over to Gunter.
Mm-hmm. Thank you, John. I'm trying to adjust that here. I can see the whole screen. I should try to get the up here. Well, I hope you can all see the screen so far, but it's still it's trying to get a different view here.
We can see your screen, Gunter.
Yeah, but I cannot see the right side because your picture doesn't. As long as okay. So thank you again. Thank you also, Stacy and Rima, for selecting me as a panelist for this webinar. It's very nice. And I was asked to talk about my encounter with nanotoxicology. And if you look at this sentence here, from accidental descriptive observations to sophisticated mechanistic and translational research, that basically summarizes my dealings with nanotoxicology. And start with the accidental descriptive observation. That was in the middle of 1980 when I was at Rochester. I joined Rochester then, and I worked with Dr. Farin. He was a refugee from the Czechoslovakia in the 1960s and had developed a technique to determine lung clearance, particle lung clearance in rats. And what he used was titanium dioxide aerosol of micro titanium dioxide, so 250 nanometers and bigger. And that was a very nice technique to determine how inhaled toxicants might affect particle clearance. At the time, I was visiting a friend in Germany, and he worked at the Degussa, former Degussa company. And I told him about our studies. He said, "Oh, we also make titanium dioxide, but a very, very fine one." So I became interested, and he gave me half a pound of ultrafine nano titanium dioxide. And back in Rochester, he also had given me aluminum oxide, another ultrafine material. And back in Rochester, Dr. Farin and we compared it then size by size by inhalation in rats to see how different they might be. And the next slide, what's going on here? Takes a while. No, that's not right. I'm not sure why I didn't advance the slide when I.
It looks like you're in another program, Gunter. Maybe if you can get out of this program.
Oh, yeah, I'm back to the first slide, and when I click here to go to the next one, there we go. Okay. maybe I just have to use the mouse. And so then when we did this study, the inhalation study, comparing side by side ultrafine and fine TI2, we were surprised to see there was a big difference in terms of the reactivity of the inflammatory response that we saw in the animals. So we put down 2 companion reports in a Journal of Aerosol Science, and the basic overall conclusions are down here from comparing the ultrafine and fine TiO2 and aluminum oxide, which at the time were called nuisance particles, of course not anymore, because the thinking was that they will not induce fibrosis. Anyway, so we saw that the toxicity of the ultrafine particles relates to their larger surface area per mass and increased interstitial access. And also the particle surface area rather than the mass should have been the proper dose metric. And other surface characteristics, for example, physical chemical ones, may modify toxicity. So these were our first results then. And in that time, the 1990s then, so that was 1990. In 1990, there was many studies came out here, and I used these studies that came out. They were done in a way using very high doses or concentrations. I used the Gartner hype cycle of emerging technologies, which has been well published, and translated that to a hype cycle for nanotoxicology. And that starts with a trigger that would be the effects of biokinetics of nanoparticles in the 1990s. There were many of those, and that resulted in a lot of misconceptions. To the top there, inflated predictions were coming out, all nanoparticles are toxic. Now this soon then was corrected there and went down to the what I call the trough of disillusionment and appreciation of reality, and which then was followed by a slope of awakening, what I call it, leading to increasing insight of nanotoxicology concepts, and then finally we are at a level of accomplishments in terms of realistic assessment of hazard and risk. And going on, I have to be careful here how. And to give you a couple of examples of what I call proof of principle or hypothesis forming studies that were published at that time here and led to this, assumption that all nanoparticles are toxic. And this, for example, on the left here, nanoparticles in some creams can stress brain cells. That was picked up by the media. Here, for example, the Munich Daily, here the Tageszeitung, coming out with the headline, "Sun cream may soften brain." And that was an in vitro study, or that very, very high doses given in vitro. The in vivo study, silicon titanium dioxide, causing pregnancy complications in mice. And if you look at the doses that were used here, 0.8 milligram nano titanium dioxide and silicon dioxide intravenously into pregnant mouse, which is equivalent to about 2 grams intravenously into an expecting woman. So you can imagine that that is not very, very good in terms of what would come out then with the offspring. And I asked a friend of mine in Germany, he likes to draw cartoons, to draw this one here, to point out the importance of exposure, dose, and response in terms of how that exposure takes place. So it starts with 2 eggs, one normally incubated by a hen, the other cooked at 100 degrees for 3 minutes, the incubation for 3 weeks at 37 degrees, and then the outcome is very different. And that is what happens, of course, with the toxicology as well, that the dose makes the poison, as we know since the 17th century from Paracelsus. But not only the dose makes the poison, also the dose makes the mechanism, which should always be considered. Now, in 2007, Vicky Stone and Ken Donaldson and myself, we published a paper on the history of nanotoxicology. And as you can see here, there are many subspecialties that go into nanotoxicology. For example, the fiber toxicology, in the role of particle shape, or biotransformation processes, the role of analytical imaging for the subcellular fate of particles, and so on. At the bottom here, virology at the moment, certainly very up to date here. The role of viruses as models for interactions of nanostructures with cells and as nanoplatforms in medicine. And then deposition studies and models, which are, now we have nice deposition models, and also the ambient PM issue, the role of small particles for systemic effects. And so that all is contained in nanotoxicology and acts as a precursor. And we subsequently published with my son and my daughter. My son is a toxicologist, my daughter an ecotoxicologist, a paper where we pointed out the emerging issue of nanotoxicology based on the study with ultrafine nanoparticles. And the following, one of the figures we had in that paper is here the exposure and biokinetics of nanoparticles here with different exposure media in the air for drug delivery being used intravenously and in food and water, clothes here. And then in general, as you see, the blood is a platform for distribution inhaled nanoparticles throughout the organism here. And translocation rates are very, very low, but it still happens. Specifically, what we are interested, and I will come to that at the end, is the central nervous system. When particles from the respiratory tract translocate to the central nervous system. The next slide shows a question that we had. Do ultrafine particles induce adaptation following repeat inhalation? And we used as a particle polytetraene particles, which we have found to be the most toxic ultrafine particle I've ever seen. We have 50 microgram exposure for rats for 15 minutes results in a lethal exposure and rats being dying. So what we did, we had 3 groups of rats, adapted, what we called them, non-adapted and controls, and the adapted were for 3 days exposed for just 5 minutes to the 50 microgram per meter cube PTFE, and then on day 4 they received the lethal 15-minute exposure. Non-adapted were just sham exposed for 3 days, and then got on day 4 side by side with the so-called adapted animals, the 50-minute exposure, and the controls were always sham exposed throughout. And the results was quite interesting. And in that the non-adapted animal all died within 3 hours. The adapted animals, when looking at the lung lavage in terms of the neutrophils, the PMNs, or the proteins, were like the controls, no significant difference, they all survived. And that had to do with the upregulation of antioxidants like metallocyanine and SOD that caused the protective mechanism in those animals here. So with the next slide, let's go to the final, and that is translocation to the central nervous system. And this shows what is known for rodent brain. Pictured in the mouse brain here. There are 2 basic pathways, neuronal pathways. One is the olfactory pathway from the nose to the olfactory bulb, the yellow part, and the other is the trigeminal pathway, the 5th brain nerve, it's pointed out here, again from the nose and oral cavity along the trigeminal, we have 3 branches, to the trigeminal ganglions into the back of the brain stem here. And if you compare then the the question is, how can we translate or extrapolate from rat studies, from rodent studies to the human? This compares the human and the mouse brain, and as you can see here, the tremendous difference is in the relative size of the olfactory bulb. The rat pretty big, and the human is the normal small size. And then there's also the trigeminal ganglion present in our species here, and we then went out to find out if indeed what we know for rodents, for mice in particular, but rats as well, in terms of translocation, can that be verified in humans as well? And we did published a study, a tissue and a review study, tissue just recently, tissue-specific fate of nanomaterials by advanced analytical imaging techniques review, and the key author here is Ushi Graham, but I should also mention Alan Dozier. He was very instrumental to get these studies going. He is at NIOSH in Cincinnati and has these wonderful ultra high resolution instrumentation to find nanoparticles in tissues here. So the high resolution scanning transmission electron microscopy together with ETH analysis and EDS analysis allowed us then to study the origin and fate of ultrafine particles in rodent and human tissues. And here is a figure here, first figure in the human olfactory bulb, and a small particle here pictured here, and here in enlarged state pictured again here. And as you can see here in this particle here, there are inclusions here, tiny, tiny particles, just 1 to 5 nanometer in size, and they consist of metals. And the next slide shows you an EDS map spectrum showing the different metals that are in this insert here, and they consist of lead and zinc, copper, manganese, and the form that we thought or they built a Trojan horse mechanism introducing those metals into the human brain via the translocation into the olfactory bulb. And so just to finish that up here, this shows a picture of the Trojan horse here that happened at the time, happily the people moving this horse with the deadly inserts into their town. That's about what I wanted to tell you briefly, and looking forward to your question. Thank you.
And thank you, Gunther. And if you can take down your slides, we're going to go to Dave Rajewski next. Dave?
Okay.
Dave, do you want to present your slides? You're on mute if you can come off mute.
Can you hear me?
Yes, I can now.
Okay. Can you see that?
Yes, if you can just hit slide share so we can see the slides better. It looks like your slide share is way over to the right,
Okay.
right? Not quite as far over to the right.
Okay, wait a second. Here we go. How's that?
Yes, that's fine. Thank you.
Okay, perfect. Sorry about that. Well, thanks for doing this. It's great to be back with all of the people that I interacted with 15 years ago. I spent some time just thinking about how to do this, and I thought the best thing to do would just go back in time and see if I could capture, because I'm not obviously a toxicologist, just capture some of the sort of the context of what was going on back then, because I forgot a lot of it. So I pulled just a bunch of slides that I actually gave at talks. One was at Harvard and one was the American Chemistry Council, and tried to get a sense of what was I talking about and how was that relevant to anything that was going on contextually. So this was 2005. You have to think a little bit about it. You know, Bush had won the presidency, Katrina happened, Tom Brady and the Patriots won the Super Bowl. YouTube was launched. If you're a Star Wars fan, you probably watched Revenge of the Sith. But this was an important point for the National Nanotech Initiative. In 2003, President Bush at that point signed the National Nanotech R&D Act. There was essentially an authorization without money. In 2005, the money started to roll. And this was the beginning of a massive amount of investment by the federal government and other governments around the world. I think in 2004, I had money from the EPA and I actually started doing work. I had some of the first meetings, I think, in Washington on nanotech that brought together the toxicology folks with industry, with environmental groups. And so that was kind of my entry point. And when I was starting to think about this in 2005, one of the things I always came back to was a friend of mine, Ed Tenner, who's done a lot of work on unintended consequences. And he always had this interesting saying that whenever we have advanced technologies, they promote self-deception. So I began to ask myself, how could we possibly deceive ourselves here? And what could go wrong? And that led to a whole bunch of questions about what some assumptions might be. I think one was that the public would accept this as markets expanded. You probably heard already, there were things coming into the marketplace, and those were getting picked up by the popular media. The NGOs would remain supportive and passive. No. I had some very interesting meetings with the ETC group, Friends of the Earth. For them, this was an incredible opportunity to sort of say, now we're releasing another set of engineered materials into the environment. We're putting them into our body. They took out the old playbooks that they had essentially perfected for GMOs, and they launched again. And they were incredibly good at messaging and getting the message across to people, far better than I was or the government was. I didn't agree with their message, but I often applauded their capacity to get it out there. So these folks obviously were kind of coming into the space and coming in fairly aggressively. Press coverage would remain fair and accurate? No. I mean, you saw what happened in Germany with the Tageszeitung and how they picked up on the science. The other thing was that the traditional press, would they even matter? Right? Where were people getting their information? 2004, Michael Crichton publishes Prey, which is about a pretty scary nanotech story. It was on the New York Times bestseller list for 14 weeks. It didn't get made into a movie, though we predicted probably 20 million people could see it based on the box office draws of Crichton's movies. 86, there was a book came out called Engines of Creation by Drexler and proposed the idea of self-replicating programmable nanobots. This gave rise to this kind of gray goo scenarios that were going to eat the Earth. 2004, Spider-Man, Doc Ock used nanotech. So what people were getting messages from was popular culture. And these were scary messages. And so, it goes back to Kai Erikson at Yale, was a sociologist, studied a lot of people's perceptions of new pollutants, and he called these new species of trouble. And nano had the potential to be a new species of trouble. when I was looking at it at that point in time. And the messaging was coming from multiple sources, not just scientists. There's this issue of, could you make analogies from sort of macro and micro scale to nanoscale? There was this whole novelty thing. At one level, people were getting the message that this was incredibly novel. We could create whole new materials, which we did. We created multiple forms of carbon. We could take a material that was inert and make it reactive. We could create this incredible amount of novelty. And so they would ask, well, doesn't that mean new risks? It was a logical step, a logical question that people were asking. And as all the stuff that we know about the macro and micro scale forms of these chemicals say anything about what's going to happen at a nanoscale. So I think that was an issue. I think it was interesting. Can we assume away the existence of black swans? These were low probability, high impact events. And we kind of stopped talking about that, but that was part of the discussion in 2005. Could these nanoparticles be used offensively in weapon systems? Could there be some sort of spill? Could there be a release? So that there, in the background, there was this kind of sense that something could go wrong, and it would be a sort of a high value and high impact event. And were we prepared to deal with that? We ran the first sets of public perception studies in 2005. We sent people all around the country. We did these year after year for 7 years. And these were some of the first kinds of messages that came out of these studies. One was the genie was out of the bottle. And this was repeated again and again in future studies, that the technology development curve was sort of outpacing our capacity to understand the technologies and their impacts. We were essentially running after the train, and this train was being pushed by massive amounts of investment, power, and politics. It became kind of a national prestige technology for the US. So this message never goes away completely. The second one is, can we trust industry?
Dave, this is John Howard. I don't think your slides are advancing on the screen.
They are here.
Well, we have a number of people in the chat box that have asked about the slides working, and I personally only see your first slide.
Wow, okay.
You may want to go out, come back again,
Okay.
and see if you can advance them. Now I see the second slide, I think.
Can you see it now?
I don't see anything on the screen right now. Now I see, I think it's the second slide.
You see it?
I see a second slide. Can you try to advance it?
Yeah. Huh. Now I can't get it to work. Oh, there we go.
No, there's just a lag. There's a lag time in this system. So it's starting to come up. I guess it's your third slide is starting to come up.
Okay. So yeah, this was I went over these assumptions, right? Can you see those, John?
Yes.
Okay,
They're
good.
coming up. I think all the bullets are maybe completed. Nope, there's one more.
Okay. Does it work now?
Yes.
Okay. All right, so let me go on. This was the public perceptions. Can you see this one?
Yes.
Okay, good. So I went through the first one, genie's out of the bottle, sort of the trust in industry. I don't think it completely evaporates. There was also this issue of trust in the regulatory system. Can't regulate it. We don't know actually what's going on, how many people actually know. And I think the last one, which continues to plague the field, was would the regulation even work, these regulatory systems? So we did a lot of analysis of the various regulatory regimes at FDA, EPA, US, all of these agencies, and drilled down on a lot of the regulations. And certainly some of them were 20, 30, 40 years old. And so there was this question about do we need new regulatory systems? It took 10 years to update the Toxic Substance Control Act, for instance, to deal with sort of some of the issues around nanotech. So these I would say these initial public perceptions don't go away. The trust in industry and the trust in government oscillates over the years, but this issue of is the technology moving faster than our understanding? Are the products coming out into the market before they can be properly studied? Can we regulate them? Will we regulate them? And who's going to regulate them? I think those continue to be part of the conversation. The other, I just want to make another thing is that we weren't alone. By this time, investors, I gave talks to investors who were trying to figure out should they do due diligence and could they invest in these companies, and also insurance companies who had to calculate the risks. So at that point in time, 2005, people were talking about 300 to 500 products on the market. We took over a database at the Wilson Center from the federal government that had about 260 products about a year later. These were products that ostensibly used or somehow used nanotech. There was also, I think, a reality gap. I mean, when people heard about this from the government, they heard about cures for cancer and super efficient batteries and paint on solar cells. And what they saw were socks with, essentially nano microsilver in them, or tennis rackets or cosmetics, teddy bears, right? So there was this kind of disconnect. And I think we never communicate to people very well about how long it takes before you go from initial investments in science and engineering to actual products and actual applications. But this was the interface between nanotech and the public, these products. And we bought lots of them, and we had, Wilson Center fashion shows and all kinds of things that we did with these. And I think this was kind of an interesting library of where nano was actually appearing. The investors were interested in existence of research. Some of that was showing negative impacts. This issue of can nano go across the blood-brain barrier? Some medical people were thrilled by that. They could deliver drugs to the brain. But there was the research, as Gunther said, the research was out there. It was often misinterpreted by the press and blown out of context. Level and adequacy of government funding for health and environmental implications research, it was pretty low at the beginning. And we spent a lot of time going back and forth with the government about how much they were actually spending. Would the regulations work? And was there any kind of comprehensive public engagement strategy to deal with these public concerns? Is it working, John, with the slides?
Yes, sir.
Okay, good. This was a big issue for companies. My friends in Intel didn't like this slide. But was it an asset or a liability? Should the companies that actually are putting this or using it talk about it? Was this going to affect their market status? Was it a propellant? Was it a barrier, hurdle? It depended on what country you're in. I mean, I think probably in Japan, it was probably an asset. It wasn't clear whether it was an asset in other countries. So this was a game we developed called Monopoly, get your product to market. And it was just a sense of just how complex this was, how many actors were in the field, what could go wrong, right? People were talking about, should there be a no nano label? What would that mean if you had a product out there on nano? What if we start putting nano into food? What kind of response would that trigger? What if there was a nanoparticle spill? How would we get the particles back? So it actually became very interesting to sort of play through various scenarios. And I found in a lot of the talks I was giving, I was talking a lot about the need to game the system, sort of think about what scenarios would happen, because there was so much uncertainty. Think about what failure modes would happen. Think about bad as well as good. Have multiple scenarios. Think about hedge strategies, so you came out ahead even if something bad happened. There was a need really to push risk management strategies to other players. We did a lot of work with small businesses. The small businesses, the startups, they had no EHS folks. Nobody was responsible, or 1/8 of an FTE was responsible. And yet they were very concerned, at least, about what were the implications of this. Municipalities, you had, places like Berkeley, California, Cambridge, Massachusetts, that were starting to regulate nanotech. So there was all these players that were out there, and it was just a mess. it was like a huge mixing bowl. And, you know, I think when I was first started working on this, it was just, how do you kind of get all these people to talk to one another? How do you kind of get the right information to the right people at the right time? How do you move impact assessments upstream? How do you bring together the people essentially that were doing the development with the people downstream that might be regulating them or trying to figure out what the damages might be? So design for environment. There wasn't a clear message. And you know, I think there's a much clearer message now, but there wasn't then. And there was no real public engagement strategy. Everybody was kind of going it on their own. So at that point in time, you know, I basically, I was paranoid, not in a bad sense, but I do think there's, when you're dealing with technologies like this and you're starting to introduce them into society, paranoia is actually useful. It forces you to focus on what you know and what you don't know. And it becomes somewhat humbling and sort of forces you to think a little bit about what you can control and what you can't control. When I moved from nanotech to synthetic biology, I became more paranoid. But I always found this was kind of an interesting sort of approach to how do we deal with the massive uncertainties when we start sort of introducing disruptive technologies into society. Nanotech project is still up there. If anyone's interested in history, and I'll stop there. John, thank you. Sorry.
Well, thank you, Dave. I appreciate it. We'll go on to Andrew.
Great, thanks, John. Dave, if you can unshare your screen, I will go to share mine. Great, just give me a second. Okay, so this is quite a strange and nostalgic meeting. I was just flicking through the participants, and it's like a 2000s reunion of everything nano. And I actually feel quite humbled sitting here because there are so many people on the call that have greater expertise than me and have contributed really important things to our understanding of nanomaterials and environmental and health sciences. But I did want to try and just give a bit of a personal story as to my background and some of the contributions here. I would also say one of the things I teach my students when we talk about communication is you've got to kill your darlings. And this is such a long, convoluted story that I've had to kill a lot of darlings in trying to tell it. So please forgive me if I don't touch on things which are important here. I would also say in terms of context, I've been trying to get away from nano for a good decade plus now. Most of my research looks across emerging technologies, responsible and ethical innovation. And I deal with much bigger issues, if you'll forgive the pun, than the really small stuff with nanotech. So this is a really interesting journey back into the past for me. So to tell the story, I actually want to start off with this 2004 paper. This was actually work that was done in the early 2000s when I really began to get involved very, very specifically with exposure to engineered nanomaterials. So on the left, you see actually a bucket of single-wall carbon nanotubes from Rick Smalley's lab. So this is work where we were asked in the early 2000s, myself and my colleague Paul Barron, by NASA to do some quality control work around some of the work that they were funding around single-wall carbon nanotubes. And we pretty immediately looked at this and thought, the problem is not quality control, the problem is inhaling those motes of carbon nanotubes that are being released. And that led to one of the first and earliest studies looking at the types of exposure we get from these materials. Really fascinating, this particular set of experiments where the first time we went down to Rick Smalley's lab, he was incredibly excited about this material. Vicky, you'll probably remember this in the early days at Rice. And he actually literally used to get a bucket of this stuff and shake it. So the whole lab was full of these motes. And he was so excitedly pointing them out to us. And us coming from an occupational health perspective, we're covering our mouths and desperately trying to get out of the room. Next time we visited, things were very, very different. Rick and the lab there learned really fast about about how to think about the public health and the occupational health aspects of these. But as I said, that was the first time that I really deeply got involved with exposure to engineered nanomaterials. But this was the result of a long journey that started well over a decade before this with my PhD thesis. So in 1989, I started working on the analysis of what we were then calling ultrafine particles at the University of Cambridge, and using this beast here. This is not me, but this is the beast that I did my PhD on, a VG Instruments HB501 scanning transmission electron microscope back in the days when everything was manual. And I was particularly interested in how we could use what were then cutting edge technologies to better understand nanoscale particles that were released into the atmosphere. So that work wrapped up in 1993, and it was published over the next few years. So for instance, one of the things that we were able to do there was to apply what were then very unique techniques to try and understand the elemental composition of very, very fine particles collected from the atmosphere. What was particularly interesting, though, was I was in a research group that were particularly interested in heterogeneous catalysts. So they were using these electron microscopes to study intentionally designed particles just a few nanometers in diameter and to try and understand their catalytic properties. So this was back before anybody was really talking about nanotechnology, apart from maybe people like Eric Drexler. But in the material science world, we were already engineering materials at a nanoscale in order to try and do things differently. Also, as a part of this really early research, it exposed me to over 100 years of work around nanoscale particles and ultrafine particles. So this is just one example. And aerosol scientists among you may recognize this. And this is actually from a paper by John Aitken back in the 1880s, where he was studying, measuring nanosized particles in the atmosphere. Of course, he didn't know that they were nanosized particles, but he was actually measuring concentrations of ultrafine particles. And he was using a device that is still the basis of how we measure these concentrations today, a condensation particle counter. And I mentioned this because this was actually part of my dissertation back in the early 1990s, looking at this 100-year history of these measurement instruments. But also, it was a really important reminder and touch point that we have actually been studying and measuring nanoscale particles for a long, long time now. And it's only recently that we started categorizing them as ultrafines or nanoparticles and getting particularly excited about them. So that was my dissertation. At the end of it, I was told, really interesting, but nobody's interested in nanoparticles. So I started studying much larger ones, but came back to trying to delve into exposure to ultrafines and nanoparticles towards the end of the 1990s. This resulted in, I think, still one of the first institutional reports around occupational exposure to ultrafines and nanoparticles. And this, it still hasn't been declassified by the Health and Safety Laboratory in the UK, but I just put this up to give you a sense of what we were looking at. So this is a study that we did late 1990s to try and understand occupational exposure to nanomaterials. You can see we use this very quaint phrase at the time, nanophase technology, which of course everybody else began to start using as nanotechnology. But I put this up just to flag that even in the 1990s, we were beginning to ask fairly serious questions about exposure to these fine particles and the potential health impacts. A lot of that came together in this workshop hosted by the Royal Society in 2000, looking at ultrafine particles in the atmosphere. But if you look through those papers, you begin to see how people were beginning to put together different aspects of research to understand the nature of nanoscale materials and their potential impacts on health. Gunther has got a really important paper in this, this collection, and a number of other people. My contribution was looking at a range of characterization methodologies which are still used today. So from there, I became increasingly interested in exposure to these nanoscale materials, whether they're intentionally formed or whether they're incidentally formed. And one of the really important things that I will still stick to is that I think sometimes there's a false dichotomy there between different types of nanoscale materials. One of the things that came out of this was the first International Symposium on Occupational Health Implications of Nanomaterials. This actually came out from an ISO working group that was responsible in the 1990s for standards around occupational exposure to aerosols. And in the early 2000s, we began to look at nanoscale materials. And we decided as we looked at this, we really needed to bring expertise together. And this ended up with this first conference back in 2004. Moving on from there, I began to get more and more interested in what was happening with nanotechnology and nanomaterials more broadly. And this is where I started working with Dave. You saw this image in Dave's slides. This is part of the collection of consumer products that we put together that claimed to use nanomaterials or contain nanomaterials in some way. I put it up because it also appears in this paper that was published in the 2000s, where I began to pull together a lot of different streams of thinking here. Not only looking at the health and the environmental implications of nanomaterials and nanotechnology, but how you fit that into a broader research context. And that, right about the same time, fed into this paper, which is still a fairly significant paper. And you'll see a number of names there, including Gunter, including Vicky, where we brought together a group of people. And again, this was under the direction of Dave Rajewski, to ask what are some of the really big research questions that have to be asked here. It was in 2006. And John, just for your reference, that is my hand in a NIOSH laboratory playing around with single-walled carbon nanotubes. So there's a NIOSH connection there. This was an important paper because we began to identify what some of the big questions are that we have to address if we're going to get nanotechnology right. And by right, I mean we ensure that we see the societal and the economic benefits of it. At the same time, we don't create something which is going to cause more environmental or health harm than we really want to see. So that was back quite a long time ago. As I said, I've moved away from nanotechnology and looked at much broader things, but I still keep tabs on what's happening. And one thing that's really interesting to me is while research into NanoEHS has continued, there seems to be far less debate around what is happening in the real world. So for instance, in 2016, I wrote this piece for Nature Nanotechnology about the material Vantablack, supposedly the blackest material ever. And what intrigued me about this, and you still see this, this is a company that was very excited about spray-on carbon nanotubes. They were basically using it as a paint, and they were putting it onto the different products to create this incredibly black surface. And I remember in the early to mid 2000s when we were talking about potential uses of nanotechnology, one of the things that a lot of people in the field said was an absolute no-no, was taking a material that seemed to have asbestos-like properties and aerosolizing it in a way that people could potentially be exposed to it. And yet here in 2016 was a company doing exactly that. And the only press coverage I could see was people getting excited about how black it was. There was no conversation at all about the potential environmental and health implications. And that actually worried me because it made me begin to wonder whether, even though we're doing all this research into NanoEHS, it's not actually translating into decisions around products. And just to emphasize that, I actually came across this in my bathroom just a couple of days ago, a spray cleaner for glass surfaces, and there right on the front of it, you've got Nanotech protection, cleans and protects. And so this leaves me with the question, what are we doing? What have we achieved? Is this product out there because we've solved all the problems around nanomaterial exposure, all the regulations are there? Or is this product here because despite all of the research that's been done and the research that's going on, nobody is really caring in the real world about what's happening? And with that, I'm going to hand back to you, John. Thank you.
Well, thank you, Andrew, and thank you for that last product placement there. So we're going to turn to Vicky now.
Great. So I will go to the board, share screen. Can you see my screen?
It's coming up, and all we got to do is hit slide share. There it is. Thank you.
All right, great. So it's a pleasure to be here, and I'll certainly echo what everyone else said about seeing old friends and thinking way back into what was going on at the start of all of this, as the webinar is called. And I just want to thank the organizers for including me. It's been really eye-opening, actually, to reflect back. Looking forward to the questions. I'll do my best to stay on time. So I want to start with where I was in the 1990s. And so this is a beautiful Ansel Adams picture of Berkeley. And in fact, I don't know if you can see my pointer, but this tall structure here just over the left in front of it is where the chemistry department was. And that's where I did my PhD. So I come from a really interesting and different background than a lot of folks I got to know in the NanoEHS world, and that I am ever since back before nanotechnology was popular, I was doing it. So I was trained as a physical chemist looking at nanoparticles. What you see here in the lower left are a bunch of quantum dots. On the left, it's blue because it's tiny. On the right, around 8 nanometers, it's red. And these materials were the subject of my PhD thesis. And really ingrained in anybody studying nano in the 80s and 90s was that the size of a material had powerful effects on its physical, chemical, magnetic, electronic properties. And that was the whole reason we studied them. And so from this, we published a paper on making light emitting diodes. I was very focused on optics at the time. And I'm proud to say I'm the proud owner of a Samsung QLED now, many, many years later. But this concept that you're working in a materials area, you're trying to make cool materials that are interesting. And, you might argue whether a QLED solves any problems for people, but it's certainly contributing to the technology that we use every day. And I think that's what motivates a lot of researchers in science and engineering, is this idea of creating materials for a better world. And that's certainly what I came out of in the 1990s as I started as a professor at Rice University. So when I started to kind of poke around, and I had a lot of contact with the environmental engineers at Rice, particularly Mark Wisner in the early 2000s, and we started to talk about how chemists make stuff that, pollutes the world, and that's terrible for chemistry. And I thought, well, nanomaterials will never do that. And then I noticed this is an OSHA MSDS website sheet about how to handle carbon nanotubes. And you'll notice here, I remember when my students brought this to me, it says elemental carbon/carbon blank is mainly a nuisance test. And I'm like, that's funny. Carbon nanotubes are not elemental carbon, or we wouldn't have just gotten several $1 million to study them from, a federal agency. And then if you looked at more and more, and I did, we started to notice that the regulatory systems that were out there were treating nanomaterials like they were bulk materials. And this was kind of my awakening moment when I really saw that there was some real big disconnect. The federal government was just gearing up for the National Nanotechnology Initiative, but their regulatory agencies were saying, hey, nano's equal to bulk, which kind of didn't make sense. And that really got me worried. I think also because I was a chemist and aware of some, chemistry doesn't have a great reputation for managing the products of its research. So I sort of developed a slide. I'm sure everybody on some fraction have seen this, the Tinkerbell side, which is that as a technologist, which I consider myself, we develop cool materials, cool molecules that solve real world problems. And that is what we promise to social society, our funding agencies, is that we're going to develop these and they're going to improve the world. And that's part of our contract. And the bad news is that in many, many cases, there are unanticipated consequences that lead to perhaps, you can argue what's the balance, but they lead to cleanup efforts later in different arenas for a lot of different people. And so I really became aware that if I was writing proposals to the US government asking for money to do technology development, I better learn quickly how to avoid the negative consequences that history had taught us happened. And how to do that is kind of the next part of my story. But I'll just say that somewhere around 2001, I became convinced that any emerging technology would prevent risk. I mean, just look at our history. And that we, and by we, I mean the royal we of the science and engineering funders and people involved in any emerging field, we are actually ethically obliged, I believe then and I believe now, to study and mitigate those risks, because we promise good things, which means we also have to put a hat on and think what bad things could happen. And that's not a terrible thing to do. That's actually part of what we should be doing. So I got very high on my horse about that. And now how do we do it? how do you actually do that in a laboratory? My laboratory is making quantum dots and, magnetic nanoparticles, and, how is that going to study risk? Well, the first thing is I got to know a number of the folks on the call is the domain experts like myself can help scope the risks. I mean, we heard Dave talk about the worries about gray goo and nanorobots in people's bodies. And it didn't take a lot of meetings to say, okay, those are maybe important social conversations, but those aren't going to be something I can test in my lab. I think the quote that I developed for communication was not in this century, maybe next century. And instead we had kind of the more mundane issues of how are we going to dispose of nanoparticles that might be in quantum dot LEDs? And what are we going to do about nanoparticles in our consumer products, as you heard Andrew talk about? And then that was really going to scope the risk for this particular emerging technology. Then you just make reasonable hypotheses. This paper in 2003, boy, I got so much negative commentary on this paper from my own community. But what I did in the paper was simply lay out, there's a couple of papers we'd published at the time about some general reasonable hypotheses for why we might think engineered nanomaterials could present environmental or human health issues, maybe, possibly, and ways that we might test them. And what was interesting that I'll share is that the community at the time, the nanotechnology community that was pushing it, the NNI folks, were not all that happy because they're like, well, you have no evidence that there's something bad. You're going to go out and find evidence. And I was like, there was a lot of discussion. In fact, Rick Smalley pulled me aside one afternoon after reading this and said, you're just throwing gasoline on the fire. And he meant the concern that people had about gray goo that you heard Dave talking about. So the nano community kind of didn't want necessarily anything to do with this. Lucky for me, there were a lot of talented risk researchers out there who had been studying inhalation and nanotoxicology, and that community was really ready to step up and become involved. So we at Rice University, through 2001, started a large center that I had the good fortune to direct for over a decade, which really centered in part on environmental implications of nanomaterials and also had a large focus on nanomedicine, so of course, human health interactions. And we tested hypotheses. We started to actually red team it. How could nanomaterials be the most dangerous things? We learned some things that in retrospect will see obvious to a lot of people. In the carbon nanostructures, the more hydrophilic, the more water soluble those systems are, the less acutely toxic they can be for interesting reasons. And also in the quantum dots, going back to the TV screens, if those particles dissolve and release cadmium, they're extremely toxic to environmental organisms. So a lot of safety by design in both of these systems is through manipulation of the surface of the nanomaterial, leaving the core material the same. And there's a lot of great work from many, many talented groups focused on safety by design and nanotechnology that really centers on how do you prevent unwanted acute toxicity and chronic toxicity if you have information about the material and how it might be used. And so what I can just conclude in this section, second message, is you really need the domain experts in the complex risk ecosystem discussions, and they may not want to be there. Depending on how the field is developing and how clear it is what the risks might be. I think in nanotechnology, that was a slow uptake and eventually is now accepted and readily looked at by the nanotechnology community, but it certainly was not at first. It was definitely seen in a negative light, in part because of the public conversations that were, to many, threatening the development of nanotechnology. That was their perception. So sort of using the discussion of risk as a balance, not everything is dangerous, not everything is safe, is sort of the goal. And I think in particular, the development of safety by design, that sort of gnome, really made it a lot easier for people to manage on both sides of the fence. Finally, I'll just sort of now as a critique, what does quality risk research mean for an emerging technology? And Dave sort of alluded to this, but what do you do when you have a technology that's not even yet in existence? I mean, how do you worry about the risk? And my argument is, well, you worry about all the good things you can do with it. So you can certainly make hypotheses about possible risk, but it's really hard to do. And as I got to know the community of EHS researchers better, what I realized is their comfort zone is in dealing with known materials, known products, known exposures. That's something they can get in there, they can measure, they can assess the risk, and they can ideally mitigate it. When you're dealing with like nanotechnology in 2000, it was not really clear what materials were going to be out there. I mean, there were already consumer products, as we found out later, that were there, but there was a lot of uncertainty in the area, and trying to fit the normal paradigms of risk assessment, which involve a lot of specificity, onto this very amorphous area was problematic. And I think that continues to be a challenge probably in nanotechnology and for anyone looking at the risk of emerging technology, is how do you do it before the technology is fully baked? And the option of just saying, we're not going to worry about it until we have a product takes us right back to the 1940s. So we don't want to do that. So that, I think, remains one of the big goals. And I'll give you one concrete example to end with. So I have had this debate at so many conferences on NanoEHS, and I'll just share it with everyone because I think it's emblematic of this early stage versus late stage risk management. So what you're looking at are some pictures of commercial nanoparticles. The one on the bottom is actually materials that we took ourselves from commercially available sunscreens. And, as a nanotechnologist, you can see this, the top one is silver. It's very, very polydispersed, lots of different sizes. The bottom one, again, it's kind of a mess. And I can take these materials and I can study various environmental or biological effects of them, but I'll only learn something really specific about them. But on the other hand, they might be similar to what's used in products, so they could have relevance. So some of the community wants to study things like this. And of course, I'm the chemist, so I'm going to make beautiful nanoparticles that are precisely controlled, and this is what I'm going to want to study, because it gives me a sense of where will I find materials that are particularly dangerous or particularly safe? So this very fundamental question about what you study is actually at this heart of how we do early stage work. So what you see here is actually some, in this particular case, it's antimicrobial studies of lots and lots of different nanoparticles. We're sort of going to libraries and big data to get better handles on the trends. But the simple picture shows you that if you want to make something really toxic to microbes, here's the structure you adopt. If you want to make them less toxic, here's this other structure. And I think that that's an important issue because none of the particles here are necessarily the ones that might be in products, which brings up the issue of knowing what is actually in products, which we still don't clearly know. In any case, that dichotomy between specificity and generality and how that fits is just one of several, I think, that sort of, you'll find in the sort of perspective and philosophies of what does it mean to do risk research in a really young technology area. So my final thoughts, I continue to think, especially as I see new technologies develop, artificial intelligence, CRISPR, the scientific community, the funding community is absolutely obligated to evaluate risk and to not wait until everything is fully defined. So we have to solve this problem more broadly. And I mean, as I said, the big we. It's going to be important that the people who develop the technology are in the room and actively involved and haven't outsourced it to the risk researchers. I think that leads to a lot less impact and a lot less influence on what gets developed by the folks making the technology. So finding ways to pull them in and keeping them engaged is important. And finally, just putting it out there, what you do for risk research and early technology is going to look a lot different than late. And that's something that I think is an ongoing question. So thanks, everyone, and I look forward to the discussion.
Well, thank you, Vicki. Great presentations all. And I want to thank all of our presenters. And I wanted to start out with a fairly large question. And it has to do with the interaction between research, whether it's intramural by federal agencies, research agencies, or extramural funded in academic centers, and the interplay between research and regulation. We have now, other than Andrew's 1880s historical anchor, we've had probably 30 years at least of looking at nanotechnology and nanomaterials. And when we look at the regulatory agencies, which are members of NNI and NEHI, on the environmental side, EPA, on the consumer side, the Consumer Product Safety Commission, on the worker side, the Occupational Safety and Health Administration, how does the panel think that we've done, and the we here is NNI and all of its member agencies, including extramural researchers, in giving to regulatory agencies the kind of science that would lead to the ultimate goal of risk evaluation and looking at the implications of a particular exposure to consumers, to the environment, and to workers, that would control those types of exposures in national regulation. So I'll start with, let's go in reverse order. We'll start with Vicki first and see if you have any thoughts on this.
Yeah, you know, my experience is I think it's been great to have FDA and EPA involved. And my only, you know, my wish is that they could be more involved. I think at the end of the day, the primary funding for the academics is drawn from NSF, NIH, larger agencies. So the ability to really connect up, and I'll take the silver example. I'm really motivated to connect because if we could predict silver dissolution in a lot of environments, then you have a sort of angle on connecting to a threshold, an exposure level that you could set in aquatic ecosystems. And so funding that, though, through conventional basic research channels is going to be really tough. And this gets back to the problem. I think regulatory science in general is just not strongly enough supported by the federal government. And I think this is a great example where you really need some research to kind of close the loop between a really huge pile of academic studies that are out there. And then, okay, how do you take that and sort of turn it into knowledge that's going to influence, hey, if you put silver in X landfill, here's what, you know, here's the limits you might face. So I think there needs to be more of it. And what they've done has been really great.
Well, thank you, Vicki. Andrew.
So I'm a little conflicted here. So John, you'll know that I predated you with the NEHI group, being co-chair of the group when it was first set up. And it was really exciting in those early days and early years where we had researchers and regulatory agencies at the table. And everybody was focused on what are the questions we need to ask to ensure that products that contain these materials and these technologies are as safe as possible. And I think that was an important and a unique part of what's happened over the last 20 years with nanotechnology. However, and I may be wrong here, and somebody please correct me if I am wrong, I think that we've seen a growing disconnect between what happens in the academic fields and academic domain and the regulatory areas. And I say this because we've developed a research funding system where to get research funding here, you've got to prove to people, you've got to convince people that there's a problem. If you're a nano risk researcher, there is no future in you in proving that something is safe. You've got to show that it's risky. And that has led to increasing research where people are scrambling to find the thing that they can show to be risky. That does not serve regulatory science. Regulatory science needs the right questions being asked and the right data and the right evidence being produced, not people trying to find the next thing that they can prove is dangerous. So somehow I think we've got to close that loop. And I may be being a little cynical here, so somebody please correct me if I am.
Well, thank you, Andrew. Dave. And you may want to come off mute, Dave.
How's that?
Yes, now we can hear you.
I think Vicki raised an important point, and that is how do you actually create a safe space for these discussions to take place between the people? Keep in mind, a lot of the academics that might be developing the products, especially near commercial products, maybe in companies. You have to deal with actually how do you get inside companies, and would they be willing to share IP with you? We did an exercise at the end of the Nano project, which was, we basically got, at the request of a bunch of large companies that were developing nano-based packaging materials for food. They said, basically, can you get a bunch of people together, the NGOs, the regulators, et cetera, and we want to have a discussion with them about things that are coming down the pike. They're not in the market yet. And we actually ran this for 8 or 9 months, and they did it by developing product scenarios. There was one way for them to share with the regulators, this is what we're going to be maybe developing, and we'd like to know how you would react to this. What kind of data would you want for us? The regulators got to look upstream, and the people that were actually developing the products got to look downstream. And it was pretty useful. It was all based on scenarios which we knew reflected pretty accurately what was actually there. though it wasn't clear what company was developing it. We kind of had to protect that. So I think we did a bunch of experiments. I did similar ones with synthetic biology. We need a lot more of experimentation about how you actually create that dialogue, because we don't know it. And I think the typical way of doing it is wait until the thing's out in the market and we have data to analyze, instead of being able to say, no, we actually have to think, much earlier. And I remember doing some work with a Fortune 500 company, and they basically told me, look, they said, bad news is good as long as it's early. And I said, geez, that's a great bumper sticker, right? Because, if it's early, then we don't have to throw lawyers at the regulators for 20 years. We haven't made huge investments. We haven't locked in the IP. And I found that actually, if you can do this successfully, it's not easy to do, right? You actually, in the case of synthetic biology, we actually had biologists go back and redesign their organisms to take risks out of them, because were in a room with ecologists who brought up potential ecological risks. They said, we can deal with that. But it was a much easier dialogue to have when they only have to redesign the organism versus having a product in the market. So I think that it's an enormous opportunity to kind of, how do you move the conversation upstream? What kind of techniques can you use? I also found that generally young researchers, young PIs were easier to engage than older ones. I don't want to generalize that, but some of the younger people actually, especially in the biotech space, have kind of internalized the sense that this is a responsibility for us. As Vicky said, no, that's part of what I'm supposed to do. And so they're actually looking for ways to figure out how they can actually get this, actually manifest this, and actually take it into the design process. So this ability to upstream, downstream, creating safe spaces, and getting people to actually redesign things. I think the other thing that's happened that makes this easier is people have focused nanotech less, but in biotech on just speeding up the design, build, test, learn cycle. So the faster you go through this, the easier it is to intervene and say, I've learned something bad in terms of the risk, now I'm going to redesign. So if you're in a very slow DBTL cycle, this is painful. If you're in one that's going very quickly, it's much easier to take the learning and put it back into the design, retest it, build it, try it again. So I think there's also, I think, some hope, and this gets back to the issue of using libraries, using robotics, using AI. All of this speeds up our ability to learn faster.
Thank you, Dave. Gunter, any comments on research versus regulation?
Yeah, I view this more from a practical side, and I think NIOSH is doing a good job visiting sites where nanomaterials are manufactured. I think of Chuck Gerazzi, for example, visiting those sites. And what I'm missing a bit is then to coordinate that better with researchers in terms of doing some toxicological studies, getting the exact material. I know also that industry is oftentimes reluctant to let people into their facilities, but that would be key to get those materials, testing them. We could even start with simple in vitro studies, but then move on to in vivo studies as well. And the most important thing is to really develop exposure dose response relationships. And Andrew is the exposure expert here, and he certainly knows that quite well, that the exposure is very important to know something about. And then also a follow-up needs to be done with respect to epidemiological investigations. Now that can take years, of course, but still some simple observation and examination of the workforce is essential to parallel that with what is being measured in the atmosphere at the workplace. So that's some brief comments about what I think needs to be done.
Well, thank you, Gunter. We have an interesting question in the Q&A box. If you were able to talk to your 2000 selves, what would you tell yourself to really focus on or not to focus on so much? And in the case of Gunter, I think we're going to have to go back a little further than 2000, maybe to 1980. Gunter, do you want to give us your answer to that? Back in the beginning, what would you tell yourself to focus on or not focus on that would be different than the path that you've taken?
You mean back in 1980, 1990, what should I have done differently?
Yes, sir.
Well, first of all, the key issue is funding. Yeah, that you need. So assuming you have all the funding that you need, that you want, yeah, I would pretty much have done more, but in the same avenue, the same line, doing studies, toxicological studies, but also get people involved from other disciplines. And that's a key issue. I think that has to be a multidisciplinary approach. So not just the toxicologists, they are one part, of course, but chemists, catalysts, physicists, physicians, they all need to get involved to tackle this issue. So again, if you have enough funding to develop a big project to do this, that would be the ideal thing to pursue then.
Well, thank you. Thank you. So we'll call your answer more funding, no regrets, except for being more multidisciplinary. So Dave, any regrets, any changes you'd make if you were way back at the beginning?
I think that one of the things we grappled with was the sense that there was a disconnect between kind of where was the pressure on the regulatory system and how much money did they have to study the risks. I always felt sorry for the Consumer Product Safety Commission because in some of the early analysis we did, it was about 60% of the things that were out there were pressing on their regulatory system. So I think if I had to go back, and I'm not sure how I would change this, obviously we could have had more discussions with the Congress, with the agencies, would be a better alignment between kind of the pressure on the regulatory system and the agencies that were actually responsible for the regulation.
Well, thank you, Dave. Andrew, we'll go back to the University of Cambridge and your PhD day to chart a different course.
With no regrets there, because I actually got a PhD and it put me on a track to a really interesting career. What I would say is my thinking has changed a lot over the last 20 or 30 years as I've been exposed to new ideas, as new evidence has come out, as the world has changed. The ways that I think about engineered nanomaterials and nanotechnology more generally has really changed quite dramatically. I'm actually quite comfortable with that because I think that this should be the process not only of science as you adjust your perspective according to what you learn, but also in terms of how we begin to understand how to develop these new technologies in a socially responsible way. That said, one of the things that I really wish that I'd pushed harder on earlier is to help people refocus from nanotechnology and nanomaterials, which increasingly I think leads to us asking the wrong questions, to talking about the interaction between biological systems and complex or advanced materials or sophisticated materials. Because the question is not what does a nanomaterial do in the body or a biological system, but how are the biological interactions that come from purposely designed materials different from what happens normally across multiple scales, and how do we begin to deal with that to ensure that these products are as safe and as beneficial as possible? That is not a nano question. It's a much broader question about materials and materials engineering.
Well, it looks like you're in the right place now, though, to answer those questions. So
yes, apart from the fact that I've got all sorts of things like CRISPR and artificial intelligence and self-driving vehicles and a whole plethora of other things on my plate.
Right. So Vicky, we're back at Berkeley with the quantum dots. Do you have any ideas about what you would have emphasized then, back then that you didn't, or how would you look at the trajectory of your history? we're going to have to learn, Vicky, by getting off mute. Otherwise,
Got it.
otherwise
Briefly,
we can't really know.
Yeah, briefly, I think the themes we've already heard, looking at where we are now, I wish there had been a way to engage the regulatory agencies way more directly in the research so that we were closer and more connected to the kinds of things they might need someday. That's something that I think was really hard to do because of the nature of those agencies and the level of funding they had and how they operated. I would say this other area would actually have been to really integrate more high throughput methodology much, much, much earlier. I think we eventually got there, but maybe, having more of that would have allowed us to start the safety by design conversations earlier than they really started happening around 2010 in earnest. So I would have pushed that much harder.
More methods development.
Yeah, all the tools you need to do it right.
Right. So one of the interesting questions also we got in the Q&A box is the role that two documents, which I vaguely remember, one from the Environmental Defense Fund and the other from DuPont, about 2006, 2007, I think somewhere around there. What kind of impact did those documents have early on? And why don't we start again with you, Vicky?
If I'm thinking about them right, they were kind of two opposing places. This was industry setting up their perspective, and then environmental defense having theirs, sort of two camps. So I think that that to me, something that I worked a lot on was how to make public-private partnerships and bring people together. And EDF was certainly in line with that. But I think those are the beginnings of that. How do we all come together, all the different pieces and look at the problem in a very sort of not an academic way, but academia, industry, and government in partnership. And I think in early stage risk research, for all the reasons we've talked about, that's really important. So those two documents, as I recall, were kind of the beginnings of bringing that to a focus.
I don't know whether Dave wants to kick in, because Dave, you were the instigator of the one framework document between the two, weren't you?
Could you come off mute, Dave?
Have the same problem Vicky does. So that actually, I went to EDF and I basically asked them to find, I said, could we develop a risk management document with a company? And I asked them, put together a proposal and find a company. So they actually produced a proposal, and they went out and had a dance card, and they had, I think, a dozen or 24 meetings with various companies. And DuPont actually was the one who agreed to work with them. And the CEO of DuPont met with Fred Krupp. It was a very high level handshake. I ended up funding EDF. I didn't want them to take any money from DuPont, right? So they were independent. They could say whatever they wanted to do. And they put out the risk document. I remember when we released it, there was a bunch of people that basically came and complained that we hadn't involved enough other environmental groups in producing this. It was kind of I think, a pioneer document. I know DuPont actually used that risk management framework to change around some of the products they were developing. It was an upstream document. It forced them to sort of look upstream at what they were doing and think about the risk downstream. It was also a time when there weren't a lot of documents like that. So it was actually used and adopted by other companies and small businesses. So I'd say that I think it was, if I look at value of investment, I think it was a worthwhile investment because it was an interesting first attempt to make this partnership, which obviously EDF had done successfully with other companies, and to come up with an actual document that provided some guidance, not only for DuPont, but could be transferable to other companies. I would say the only downside was it wasn't a document that could be easily adapted by a small business, right? Because it wasn't designed by small business. DuPont obviously had some significant resources they could throw at the problem. But I think the general kind of process they went through, sort of the thought process, was actually useful for companies, smaller startups.
Well, thank you, Dave. We're coming to the end now. We've only got a couple minutes left. So my last question is for Andrew, who is now specializing in these broad areas of emerging technologies. How good, how well, how successful do you think this early NNI structure, NNEHS structure of risk evaluation, risk governance, has that been a good exemplar, a good pattern that can be applied to other emerging technologies? What kind of a grade would you give us for that?
In the early years, I think it was incredibly important, and I'm really proud to have been a part of those early discussions, simply because it got different players together in a completely unique way to address what seemed to be an important and emerging technology. If I was honest, I would say that sitting outside of the nanotechnology field these days, the impact seems to be somewhat marginal. I see conversations within the nanotech community that really do not translate outside. And as a result, when you see the bigger conversations around emerging technologies, all the way from domain-specific stuff around AI, synthetic biology, other areas, all the way through to overarching stuff like the fourth industrial revolution and convergent technologies, I see virtually nobody taking the lessons from nanotechnology and applying them. So I think we started really well, but I think there's a lot of work to be done to translate those early lessons to how we deal with new technologies more broadly.
Well, thank you. Thank you for that answer. And I want to thank Gunter and Dave and Andrew and Vicky for excellent presentations. And I wish we had even more time for Q&A. We've had just exchanged a lot of valuable information, great discussion, and thanks everybody for tuning in to this webinar. We hope you'll join us on March 23rd at noon for the next webinar in the series, which will address what we have learned in the realm of human exposure. So again, if you're interested in our series of webinars, we invite you to follow us on Twitter at NNI Nano News and check nano.gov for more information. We're just really blessed by your interest in the webinars, and thanks again to all of you great panelists for this walk back in history and leap forward to the future. So thank you everybody, and have a great rest of the day.